This is Needle 2. It's a 14 megabyte agentic LLM model. Let me repeat that in case you missed that. It's 14 megabytes. And it has 45 million parameters. Basically, this LLM is so tiny, it can actually run on any edge device down to a bare ESP32S3. It was developed by Cactus Compute, who have now open sourced this model under the Apache 2.0 license, and I tested it myself, and it actually works. So in this video, we're gonna take a look at Needle 2, see how it works, and then we're gonna run some fun inference tests on an actual microcontroller to see how it performs. It's gonna be a lot of fun, so let's dive into it. So a couple of weeks ago, I did another video where I deployed a 29 million parameter model on an ESP32S3, but that was more of a gimmick and not an actual LLM because it was so bare bones, it was trained on children's stories, so that's all it could ever output. This LLM, however, is an actual model that understands your context. But before you get too excited, there is a caveat to it. This is not going to be your regular chatbot LLM. Instead, this model is specifically made to work as a tool call dispatcher. So the way it works is that you predefine a set of tool calls, and that could be anything from rotating a servo to any other mechanical or executable operation that you can think of. And then you can prompt the model in natural language, and it will be smart enough to understand based on your command which tool call to execute. And that's basically the gist of it. Now this is really cool because on a board like a Raspberry Pi 5, it can achieve up to 500 tokens a second. So it can be a very efficient driver for, let's say, robotics projects. But on bigger, more performant devices, can Needle 2 actually operate as a chatbot? Well, the answer is no, because it's not really a speed question, because Needle wasn't trained on general knowledge or conversation at all. Its entire training data is device actions like smart home commands, mobile actions, wearable actions, that kind of stuff. So even on a beefy device, if you ask it what's the capital of France, it won't be able to answer. It's going to be really good at picking the right function and filling in the right arguments, but that's it. And that's the trade-off they had to make to get it this small. But let's actually talk about how they pulled off 45 million parameters that are actually competitive with models 5 or 7 times bigger. Because normally when you shrink a model that much, it just gets dumb. But Cactus didn't want that, so they rebuilt a few pieces of the architecture from scratch. So the big change is something they call an n-gram. Normally, all the model's knowledge lives in its weights, and every single one of those weights has to be run through a matrix multiplication for every token, and that is expensive. But Cactus moved a chunk of that knowledge into hashed lookup tables instead. So the model can just go grab a row of memory instead of doing math on it. And they also swapped the normal MLP layers for something built on a Hadamard transform, which is a fixed mathematical operation with almost no learnable parameters attached to it. Normally, that mixing step is done by huge matrices that the model has to learn from scratch, and that eats up most of the small model's parameter budget. But a Hadamard transform skips all that learning because it's a fixed formula that does all the mixing for free. So Cactus gets that benefit without spending any of their 45 million parameters on it. And then there's quantization, which honestly is the part that makes all of this deployable at all. Needle 2 runs on 2 bits per weight, and it was actually trained on 2 bits, not quantized down after the fact. The problem is that a lot of small models fall apart when you compress them post-training, because they were never built to survive that compression. But Needle was trained against its own compression from the start, so their default version is already optimized. So does any of this actually hold up? Well, on Cactus's own benchmarks, Needle 2 is genuinely going head-to-head with a model 5 times its size, and on a couple of the harder tool calling tests, it actually beats it outright, despite running a 2-bit precision against LFM's 2.5 full 16-bit precision. And on the mobile actions benchmark, Needle picks the correct function name 98.3% of the time, and that's higher than every single model it's compared against. So it's not perfect at everything, but the job it was actually built for, it's really, really good at. that. So let's test it out to see how it actually works. So for this purpose, I built my own custom inference engine that actually runs on this exact board, an ESP32S3, and I'll leave a link to the GitHub repo in the description below if you want to try it out for yourself. So here in the terminal, we can see that we have a little TUI application. So now I can just prompt it with a natural language request and see how it works. So first, let's prompt it with something simple. Let's say to flash a red light for 3 seconds. And as soon as I launch this, you can see it's mapping the model straight off the flash chip and setting up its working memory. And once it has done so, it goes through the reasoning phase, and we can see that it identified that the color is red, the mode is flash, and it also identified that we need to do it for 3 seconds. So once it's done with the reasoning phase, it will proceed to writing the actual tool call. And this takes a bit of a moment because it is slow on an ESP32, but nonetheless, this is pretty cool. And look at that, we now get a flashing red light for 3 seconds. And we can also see that it has a confidence score that tells us how confident it was about this particular tool call. And this is built in Needle 2. And this is pretty cool because based on this confidence score, we can program the chip based on different scenarios. So as you saw, this took about 39 seconds to complete, which might sound slow, but remember that this is a 45 million parameter model running on an 8 megabyte microcontroller with no GPU. Now let's see what happens if I ask it something totally out of context. So let me just ask it, what is the capital of France? And as you can see here, it's reading our request again. And now in the reasoning phase, it says that there's no tool available for country facts. So the tool call is going to be empty. And look at that. It was very confident that there are no tools that can confidently be executed based on this prompt. So I would say this is still a very intelligent response. This time, let's ask it to shine a purple light for 7 seconds. And let's see if it understands that. And it identifies that color is indeed purple. And it understands that shine means that the mode has to be solid and not flashing. And it also understands that it has to be for 7 seconds. So then it proceeds to write the actual tool call. And once it has done so, look at that. It's now shining a purple light. Should be 7 seconds. There you go. How cool is that? And interestingly enough, this time it wasn't as confident. So the confidence score was 0.57, but it still managed to reason through the task accordingly and execute exactly what we asked. And there's one more thing I want to show you. I built this project specifically to be reusable, so you can swap out the flashing light commands for something else. Like for example, if you have a robotics project that is using servos, you can basically replace these commands with your own. And I've documented a 3-step process how to do that in the project's README file. So if you want to reuse it for your own projects, just follow those 3 steps and you're good to go. Let's try another variation. Display a yellow light for 5 seconds. And there you go, it's flashing a yellow light for 5 seconds. And this had the lowest confidence score of them all, 0.46. And I found interesting that it thought that displaying meant flashing a light and not displaying it for a prolonged period. So there you go, that shows that the model is not perfect. It might still misunderstand your intentions, but nonetheless, we got a yellow light and we got it for 5 seconds. And most of these tool calls take around 40 seconds to process with 1.86 tokens a second on average. So that is a pretty cool result in my opinion. So there you have it, folks. That is Needle 2 in a nutshell. A 45 million parameter model, 14 megabytes, running completely offline on a chip that cost about $10. And folks, if you like these types of technical breakdowns, please let me know by smashing that like button underneath the video. And also don't forget to subscribe to our channel. This has been Andres from BetterStack, and I will see you in the next videos.